Greetings, everyone. Happy Friday. Welcome to today's IWCS webinar. We're going to give folks just another minute or so to join in, those who are fashionably late today. So just sit tight and we'll get started. Again, we want to thank you for being a part of this from wherever you are. I saw the registration, and I think we're in all corners of the globe. So good evening. Late into the evening in some places, good afternoon and good morning. So here we are. For all of us, the good news, it's Friday. All right. Well, why don't we go ahead and get started? There may be a few more joining us, but let's get started. So again, welcome to today's webinar. My name is Dave Cadu, and I'm honored to be the CEO of IWCS, and I'll be your moderator today for the IWCS webinar series event. Just a few housekeeping items, as always. Please note that as an attendee, you're part of a larger audience, and during the presentation, all participants will remain in listen-only mode. And also, as a reminder, we are recording the broadcast for rebroadcast on our website, so you and your colleagues can go watch it at your leisure if you wish down the road. We encourage you to submit written questions at any time during the presentation. So as our presenter is speaking, just use the chat panel on the right of your screen. After typing your questions in the space at the bottom, just hit the send button and your questions will be addressed time permitting at the end of the presentation. So today our IWCS webinar series event is hosted by the Cable and Connectivity Industry Forum. And today we're honored to have Michael Dodds, who is a test engineer in the Systems Verification Lab for Leviton. He's located in Pennsylvania, USA. And Mike will be presenting his paper on channel performance degradation from installation stresses. And I want to make note that Mike received the Best Presentation Award at our IWCS 2023 event in Orlando, Florida last October. So again, we're very thankful that that Mike is presenting this to us today to our larger global audience. Mike is currently a test engineer at Leviton's Systems Verification Lab in New Holland, Pennsylvania, where he researches both fiber optic and twisted pair communications. His research focuses primarily on the effects of Ethernet link segments on real-world Layer 7 performance. He received his Master's of Science in Electrical and Biomedical Engineering from Drexel University in 2017. So Michael, welcome, and thank you for presenting at today's IWCS webinar series event. So take it away.
All right, yeah, thank you, David. Good morning, everyone. Thank you for joining us this Friday. Today, as David said, I'm going to be presenting on the topic of installation robustness. That is how well certain types of cables can resist common installation stresses that occur when you're pulling a cable into a horizontal cable into your installation. So we're going to start off with a brief introduction regarding the types of installation stresses that were evaluated in this study. Next, we'll pose the questions that we hope to answer with this study. And I'll explain how we investigated these questions, and then we'll get into the results and the conclusions that we can derive from them. The images there on the right are basically just previews of the types of installation stresses that we'll be looking at in this presentation. We'll also be getting into different termination effects. That is how you connectorize a cable with different jacks in a permanent link. So, and the effects that can arise from that in terms of your system performance. So 3 of the more common types of physical insulation stresses that you might experience in the real world are tension, crush, and kink. Tension, as the name suggests, can just be thought of pulling the cable with too much force. And there's a number of different things that can cause this. It could be just excess drag being caused by the conduit that you're pulling the cable through, or it could be being caught around an edge of a bend in your installation, or just various other types of friction causing um, uh, anomalies that could occur during your installation. There's also crush, which will be defined as exerting excess compression on a single point within the cable. As you can see in the picture right there, basically just compressing a single point of the cable, crushing down uh, the geometry of the cable down to, let's say, a more flattened state. And then lastly, we'll be looking at kink, which is basically just inducing a harsh bend radius violation and effectively pulling that into a kink, as the name suggests. So just basically pulling it into a loop and then closing that loop with pulling during installation. So as I mentioned before, tension can be induced by pulling the cable over hard corners or edges, or by yanking the cable when beginning the pull. The industry recommendation for when you're installing cable is not to exceed 25 pounds of pulling tension. If you do that, you're going to start seeing the geometry of the cable being deformed, and you'll get all sorts of issues when it comes to internal crosstalk and return loss, and different avoidable issues if you were to stay underneath that 25 pounds pulling tension. Um, as I said, if too much tension is applied to the cable, it could result in the jacket weakening or the pair geometry deforming within the cable itself. And if the geometry of the cable pairs is deformed too much, you can see significant negative impacts to your impedance, which will affect your return loss and your crosstalk, which ultimately feeds into your system performance. It can cause drop frames in your application, depending upon what type of application you're running. It could even lead to various safety violations. If the jacket becomes too thin, you might get issues with the flame rating and different issues like that. So effectively, what you want to do is you want to reduce the amount, or you want to stay underneath that 25 pounds of pulling tension. But in the real world, that's not always the case. And what we want to do is we just want to illustrate what could happen if you go beyond that level of tension. So crushing and kinking are also both common single point defects that occur during installation. There's a number of different things that could cause crushing of a cable. One source of it could be a reel just accidentally rolling over top of a cable that's been laid out on the floor, or you could just have a worker who just, unbeknownst to them, accidentally walks over it, because in workplaces, a lot of times you might just have horizontal cable laying out on the floor, getting ready to be pulled into a conduit. So depending upon the work environment, there are many different sources that could cause the crushing or kinking of a cable. But the important thing is remember that they're effectively just single point defects within the cable, and there's a number of different issues that this could cause. So single point defects like crushing or kinking can effectively cause ringing effects across the frequency band, which will ultimately negatively affect your application the same way that excess tension would. And again, what we're hoping to analyze with our study is to see what kind of negative effects crushing and kinking can have on your application performance. Another crucial facet of proper installation is the effect of proper or improper connectorization. That is, how you terminate a cable to a jack. There are other types of terminations that we could look at in terms of plugs or consolidation points, but for our study, we just looked at terminating with 110 style punch down jacks, just to kind of normalize the connector that we were using. So intra-pair separation, or the interweaving of individual pairs, can lead to increased crosstalk. And a lot of times the connectors will be near the endpoints of a channel. So if you have bad connectorization, this can lead to significant degradation in your performance. So effectively, these issues that you have at the connectors will probably be the loudest in your overall channel performance. So little issues when it comes to connectorizing your cable could lead to bigger issues down the road just by improperly connecting your cable to your jack. We just a couple different images there of different types of issues you might see um, with your connectorization. So I'll get more into this later, but just to zoom in a little bit, effectively, What you have here on the left-hand side is excess pairs being pairs being excessively untwisted outside of the jack, not being terminated close to the connector point as the manufacturer recommendation normally is. And then what you have here is it's a little difficult to see, but with the blue pairs and the orange pairs is pairs interweaving with one another. And again, that can negatively affect your impedance, which will in turn negatively affect your crosstalk, negatively affect your return loss, and that'll cause all sorts of issues down the road. So again, that brings us to the two main questions that we wish to answer with our study. And number one is, how do these various installation stresses affect cable performance, that is passive cable performance? And number two, how does connector termination affect the overall channel performance? And we also look at permanent length, just a way of kind of narrowing in on the effects of the connectors. So if we got to our test setup, the test set that we looked at was approximately 150 cable samples that were subjected to a harsh installation test, which I'll get to on the next slide here. The test consisted of 22 different cable types from multiple manufacturers. We looked at 5 different Cat6 cables with cross fillers, 10 different Cat6 without cross fillers, 3 Cat6As with cross fillers, and 4 different Cat6As without a cross filler. So effectively Cat6 and Cat6A with or without a cross filler, just to see if that extra bit of maintenance on the internal geometry of the cable, if that helps make it more robust to installation stresses, or if there's other factors at play that can help mitigate these kind of stresses and reduce the chances of you having negative effects to your crosstalk or return loss from harsh installation. So this is a diagram of the harsh installation robustness test that we subjected the cables to. So we had multiple samples of each cable type that were pulled through this installation robustness fixture, and it consisted of multiple stages. So we started off with a baseline measurement of the cable under test on an accumulator, just to see what the cable status was before any kind of harsh installation was, before it was subjected to any kind of harsh installation. Then next, we pulled it through a pulling fixture, which included a tension rig and a different drag fixture. So effectively, these are simulating basically the cable being caught around harsh bends and the tension that can arise from that, and also if the cable's interweaving between different points within the area where you're pulling the cable, any kind of tension that could be induced from that. So together, these kind of give you the tension of the cable being interwoven between different parts of your conduit run or whatever run you're running your cable through, and the cable being bent around edges and the friction that can be induced from that. So after that, it went through a crushing fixture, which is effectively after the cable was pulled through the drag fixture and the tension rig that we have on the left here. That sample was rolled over with a fully loaded cable reel with thin flanges, just to kind of simulate what the worst case scenario would be in terms of a cable reel rolling over a cable. And we wanted to normalize it, so we kept it as we have a standard cable reel that we'd use for this for the testing, because we didn't want to have the repeatability issues with simulating a person walking on it, because there's different kind of angles that people could step on a cable, people might be different weights, but we wanted to normalize the test across our entire study. So we use a single fully loaded cable reel with thin flanges, just to keep things standardized across all of our different test samples. And lastly, the cable was kinked. So as you see here, a loop was pulled, a loop was induced, and then we pulled it to induce a kink on the cable. It's just a pretty straightforward test. It's a harsh bend radius violation, and then we close the loop by pulling it just to induce a kink within the cable near the endpoints of the channel. And each sample was tested after being pulled through each of these individual steps. So we tested it at baseline, we tested it after pulling, tested it after crushing, and tested it after kinking. So we basically have samples of what the cable performance was after each individual step of the installation robustness test. In terms of the connectorization studies, in order to evaluate the effects of jack termination on channel and permanent link performance, we looked at 4 90-meter category links, and we tested them in multiple ways. So first, we got a baseline by connectorizing the cables per manufacturer's instructions, just following everything by the books, making sure there was as little untwisted outside of the jacket as possible, making sure that the cable was as close to the punch down tines as possible. And then we did a second test where the pairs were exposed outside of the jacket, but they weren't untwisted. So that's what you see right here in the second picture. So pairs outside of the jacket, but not untwisted. And then we exposed the pairs outside the jacket and untwisted them. So same thing as the previous test, but we just untwisted them. So they were just effectively 2 copper conductors, not intertwined with one another, just running alongside until they got to the termination points of the jack. All right, and then the fourth picture there is we induce irregular loops within the connector body. And this one's a little bit more difficult to see, so I'll try to zoom in and make it a little bit clearer. But effectively what this was we gave more slack for individual conductors within the connector body. So if you see this white pair, this blue pair right here, rather than going directly to the tines, they effectively loop around within the connector body before going to the tines. So you effectively get a little bit of crosstalk being induced on that individual pair going back to itself. And then lastly, a fifth part of the termination study was we tried other category compliant jacks following their best practices, just to get an idea of what kind of variation you can expect by using different jacks for your channel or permanent link. So if we get to the results. All right, on this slide right here, we have the time domain return loss measurements before and after the cable samples were pulled through the installation robustness fixture. So what we see at the baseline here is that it's a pretty clean trace. You will only really see the return loss spikes here at the ends of the permanent link where you would expect them to be, where the connectors are. But then after harsh installation, what you see is the portion of the permanent link that was being pulled through the tension rig and the drag fixture. You get all these different return loss spikes happening within that run of the cable. And additionally, at the areas where the cable was crushed and where the cable was kinked, you see different return loss spikes, which reflects what you would expect in the real world, because you're deforming the cable, you're inducing single point defects. So you would expect for there to be change in impedance at that point of the channel. So change in impedance would give you return loss as part of the equation. So it's pretty logical to see those kinds of phenomenon happening within the cable after crushing, kinking, and pulling it through our robustness fixture. All right, and on this slide right here, we have a comparison between Cat6 cables without a cross filler and Cat6 cables with a filler. And what we see in these 2 graphs right here is relative to baseline. If we look at the Cat6 without a cross filler, there's a reduction in the population crosstalk after pulling it through the drag and tension rig, and after crushing it and after kinking it. So there's a pretty significant drop off from the baseline after pulling the Cat6 without a filler through the pulling rig, after crushing it, after kinking it. But the Cat6 with a filler, it effectively stays at that baseline even after pulling it through the tension rig and the drag fixture, and then crushing it and then kinking it. So this is just kind of showing the difference between a Cat6 cable without a filler versus a Cat6 with a filler, and the kind of robustness that it has relative to these installation stresses. But that's not to say that the presence of a cross filler guarantees that you'll have a more robust design. There are other design features like the tightness of twists and the material properties that can mitigate installation stresses. So there's not a clear differentiation between any cable that has a filler versus any cable that has no cross filler, and that being more robust to these installation stresses. Effectively, it boils down to the resilience of the cable itself, which can be summarized from the twisting of the paralays, or the jacket material. Effectively, how strongly can it resist these geometric deformations being caused by these installation stresses? So that can be mitigated by a cross filler, but a cross filler isn't exactly a magic bullet to make sure that these kind of installation stresses will never be an issue. So many different factors can be a part of resisting these installation stresses. So it's not as simple as just a one design feature fix. And when it comes to connectorization, we notice a few different trends. So on the top row there, we have the baseline, average, channel return loss, channel next, permanent link return loss, and permanent link near end crosstalk margins. And then if we look at the rows 2 through 4 underneath of it, we can see the effects of exposing the individual pairs outside of the cable jacket, but not untwisting them. As we can see, there's not really much of a difference between exposing the conductors versus keeping them within the jacket. But if you untwist them, you see a pretty significant drop off in the average return loss margin, the average next margin in both channel and permanent link. And additionally, you see the same kind of issues pop up with crosstalk in channel and permanent link measurements. So if you induce these irregular loops within the connector body, like we showed on the previous slide, basically looping the individual pairs back around on each other within the connector body, you're going to see these issues pop up for channel crosstalk and permanent link crosstalk. And if we look at rows 5 through 7, so the last 3 rows there on the bottom, what's interesting to point out here is basically following the different manufacturers' instructions to a T and just using different connectors for different cables. And what we can see is that depending upon what connector you use, there can be a pretty significant difference in terms of your channel return loss, channel next, permanent link return loss, and permanent link near and crosstalk. So the important thing to remember here is that not all jacks are manufactured equally, and it's pretty important to make sure that you match up the proper connector with the cable that you're using in your installation, because otherwise you could have the exact same cable, you passing its relative spec with plenty of margin with one jack, but then as soon as you change it out to a different jack, following all the manufacturer's instructions, all of a sudden you're looking at negative 10 dB of margin. So choice of connector is very important. So in summary, we can draw a number of different conclusions from our analysis. First, cable design significantly affects the robustness, the overall channel system's robustness to installation stresses. Cables with cross fillers tend to be more robust, but the presence of a cross filler isn't the sole determinant. Like I mentioned before, there are different facets that can make cables resilient to these installation stresses, such as the jacket properties, the compounds used within the cable itself, the lay lengths, how well the cable's twisted. But what we did see as a general trend is that Cat 6A cables are generally more robust than Cat 6 when it comes to resisting installation stresses. And like I said before, this is probably due to the tighter twist and the shield or isolation wrap of the cable, kind of helping maintain that internal geometry and sort of keeping everything together in the original geometry that the cable was designed for. So when lacking any kind of shield or isolation wrap, or with having loose lays, any kind of dragging or crushing, any kind of like single point defect could cause the geometry to deform pretty dramatically. And in turn, you deform your geometry, you're going to change your impedance. Changing your impedance, you're going to get decreases in crosstalk and return loss margin. Secondly, the quality of the connectivity that you use matters. As we showed on the previous slides, you can have a pretty dramatic change in your crosstalk or return loss margin just by changing out what connector you're using for your channel. You can follow the instructions to a T for the connector that you use, but if it's not really properly matched to the cable that you're using, you can run into all sorts of issues with impedance mismatches, which in turn can cause you to have crosstalk or return loss issues. So it's very important to make sure that you're choosing the proper connectivity for your channel. And also sloppy connectorization can also lead to failures. So even if you choose the right connector, if you're not terminating it properly, if you're rushing through your connectorization and you're kind of cutting corners, you're going to run into these issues where a connector and cable pairing, which otherwise would be perfectly fine, is all of a sudden giving you issues in terms of crosstalk and return loss. So you want to make sure that you're taking your time, following the manufacturer's instructions properly, and not cutting any corners. So lastly, and I've alluded to this before, but probably most importantly for a lot of the people here, is that choosing robust cable and components and properly connectorizing your system will save both time and money in the long term. So while you might be saving money in the short term by purchasing cheaper cable or by rushing your connectorization, it could come back to bite you in the long term, causing you more than you saved in the first place. So it's a bit penny wise, but pound foolish when it comes to cutting corners in your installation. So you really want to make sure that you're choosing the proper cable, you're choosing the proper connectors, and you're properly installing both of them. So properly connectorizing your cable, properly installing your cable, properly connectorizing your cable, and properly pulling your cable through your installation medium, and also choosing a cable that can be resistant to these kinds of installation stresses. So just remembering that proper choice, proper installation are very important, can save you money in the long term, even if it might cost you a little bit in the short term. So with that, I want to thank everybody for your time. And with that, I'll happily take questions if anybody has them.
Mike, thank you again for that excellent presentation. Some real practical and real world issues that need to be addressed, and clearly, we put in sophisticated network systems, and they can be defeated quite easily by poor workmanship or damage.
Yep.
You might want to answer this question two different ways, but noticing the connectorization issues and kind of separating the twists and the pairs, and also looking at damage, crush, kinking, things like that. I know that you focused on near end crosstalk, but have you looked at the actual attenuation and loss of data, and what impact it might have on transmission speeds?
We haven't looked at it with these specific samples that we use for this study, but we do a lot of kind of layer 7 testing in our lab with cables that have been subjected to these kinds of installation stresses, and it really depends on the degree of the damage that's being done to the cable. So in some cases, you might effectively active equipment, they're not being designed to be minimally compliant. So there's always some kind of headroom that's built into it that can compensate for a bit of less than ideal margin when it comes to your system. So we have looked at it. Again, it depends on the severity of it. I mean, if it gets beyond a certain threshold, you're going to start to see visual degradation in your channel performance. But even if you don't, it doesn't necessarily mean that it's not an issue. So if you all of a sudden might be failing crosstalk by 2 dB, and you think, and it's with any pair of active equipment, you might be able to transmit without dropping any frames by kind of piggybacking off of the margin built into the active equipment. But you could have any kind of elevation in temperature or any kind of other installation stress being induced to it, and all of a sudden your channel performance is gonna fall apart. So it's really important just to make sure that these stresses are mitigated as much as possible, because even if it seems to work in the short term, you don't know what the conditions of your installation are going to be in the long run, and that could lead to catastrophic failures down the line.
And I know it may be a whole nother investigation, but any conceptual theories on the impacts for powering, over Ethernet, links, and if you have these damages, or even at the connector where it's not, connected correctly, you're going to find any kind of, I don't know, arcing or any kind of power dissipation that might cause problems.
That could definitely be an issue, especially if the installation of the conductor is kind of pinched or scraped by crushing or kinking, or even if it's pulled thin with excess tension during installation. That could definitely be an issue. And also you could have just increases in your channel DCR just by physically damaging the copper conductors within the cable. So yeah, it could definitely negatively affect your power over Ethernet performance. We didn't look at that specifically, but I can definitely see a world where that's an issue.
Well, all the more importance, years ago, all we were looking at was data, and now
Yep.
clearly the convergence of putting power and data, limited energy across these same cables, it becomes that much more important. Workmanship, handling, and particularly counterfeit cables and copper clad aluminums and everything else. We really have to be that much more diligent and careful.
Yep.
Has testing been conducted to see any of these kinds of effects on patch cords?
We didn't look at that with this study, but it would. I'm sure that the stranded conductors might make it a little bit more resilient to different types of insulation stresses. We didn't look at that specifically, um, but it would follow kind of the same kind of practices where you don't want to pull it too tightly, or you don't want to induce bend radius violations and kink it or crush it, because even though you might be using stranded conductors instead of solid conductors, you could run into the same kind of issues where you're thinning out the conductor insulation. And if your PoE system, if you're using a patch cord rather than any kind of like direct attached to your horizontal cabling, again, you could have arcing just by the conductor insulation becoming too thin, or you could have DCR increases. Maybe some of the stranded conductors are frayed by crushing or kinking. In which case, you run into the same kind of issues. We haven't tested it, but it would just kind of be, I think it'd be sort of a different avenue by which those issues arise with stranded versus solid conductors.
Right. What procedure or selection process should be used to match the cable to the connector? Is there a total performance measure or testing that you can make sure that you're selecting the right connector?
I mean, probably the best approach to make sure that you're getting things that are properly paired to one another is to look at a whole system. Basically trying to find a whole system end to end that's suitable for your installation, rather than picking out maybe a cheap horizontal from one place and a cheap connector from another place, and kind of hoping that they terminate well together. Going with a reputable manufacturer who's actually tested different connectors and cables being paired with one another, and they're aware of what the end to end system performance is going to be. So I would say, yeah, going with a full end-to-end system would be a good idea to make sure that you're getting proper pairings of connectors and horizontal cabling.
All right. Any experience with tight bend radius, than what would be typically recommended? I mean, how far can you push the bend radius value? I mean, you get to a point of kinking, I'm sure, but
Yeah, yeah.
yeah.
I mean the industry guidelines, they exist for a reason. We would never recommend going beyond the what the industry guidelines say in terms of in terms of the bend radius. And again, it all depends on the design of the cable itself. Maybe the cable has very tightly twisted pairs, and your bend radius violation might not generate as degradative of a effect as it otherwise would for a cable with looser lay lengths. So again, we wouldn't ever recommend going beyond bend radius violations, but in the real world, they might happen. Uh, in which case, the cables with the more robust internal geometry would probably be more resistant to those kinds of effects, as based on what we saw in our study.
Great. I don't see any more questions unless we get a last minute question. Uh, we'll keep an eye just here as we wrap up. But I'm going to be sharing now on your screen just in just a second here. Here we go. So I'm sharing with you the contact points so that if you wish to reach out to Mike offline, feel free to do so. You can make note of his email address here. And again, we want to thank Mike for presenting this, very important and real world presentation today, so to help us, understand about the pitfalls of good practice and best practice if we don't adhere to that. And again, please note the contact points in case you wish to reach out to Mike. Each of these IWCS webinar series events are recorded and are archived on the IWCS.org website. So it normally takes up to a week or so to have these posted, so that you can share it with your colleagues, or if you wish, you can watch it again. The IWCS webinar series will conduct technical paper presentation webinars, as well as some sponsored company events several times each month. And our next scheduled webinar will be on Tuesday, February the 27th. That's just in a week or so at 10:30 a.m. Eastern USA time. It will be by Techno Apex on reimagining fiber optic cables with materials innovations. And then the subsequent technical paper presentation webinar event will be on Friday, March 15th at 10:30 a.m. Eastern. We typically have the technical presentations the third Friday of each month. Each of you will be receiving an announcement for these events, so please feel free to share them with your colleagues so that they can join and register as well. I don't know, Becky, do you see any last minute questions for Mike?
No, I do not.
Oh, very good. Okay. Well, again, we thank you all for participating. Before we conclude, however, I want you to make sure to recognize our IWCS partner sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, thank you to these leading suppliers in our industry for your support. And very importantly, went the wrong way. Rapidly approaching is our next 73rd annual Wire and Cable and Connectivity Industry Forum. It will be in Providence, Rhode Island, a popular venue for our event in October. And we hope that you and your company will consider exhibiting as well as presenting technical papers, the good work that you're doing to bring new innovations and products to our industry, as well as to attend and to network with your colleagues from around the world. Abstracts are in the process of being collected. So we hope that you will consider submitting an abstract. The process is very easy. Just go onto our website and IWCS.org/present, and you will find a template, again, one-page abstract by early April, and then we will generate the program and the technical sessions and place your paper accordingly. So please consider doing that. Already we're getting a very, very strong response, so we expect it to be a very strong conference in October. So we hope that you'll join us and present as well. So again, want to thank Mike for joining us today, and for all of you. And we hope you have a great weekend, and look forward to seeing you at our next webinar. Thank you.